factors involve comparisons of the same subjects under different conditions. For example, in the ADHD treatment study, each child's performance was measured 4 times, once after being on each of 4 drug doses for a week. Therefore, each subject's performance was measured at each of the 4 levels of the factor dose. Note the difference from between subjects factors, for which each subject's performance is measured only once, and the comparisons are among different groups of subjects. A within subjects factor is sometimes referred to as a repeated measures factor, since repeated measurements are taken on each subject. An experimental design in which the independent variable is a within subjects factor is called a within subjects design. An advantage of within subjects designs is that individual differences in subjects' overall levels of performance are controlled. This is important because subjects invariably will differ from one another. In an experiment on problem solving, some subjects will be better than others, regardless of the condition they are in. Similarly, in a study of blood pressure, some subjects will have higher blood pressure than others, regardless of the condition. Within subjects designs control these individual differences by comparing the scores of a subject in one condition to the scores of the same subject in other conditions. In this sense, each subject serves as his or her own control. This typically gives within subjects designs considerably more power than between subjects designs. Let's consider how to analyze the data from the ADHD treatment case study. These data consist of the scores of 24 children with ADHD on a delay of gratification task. Each child was tested under 4 dosage levels. For now, we will be concerned only with testing the difference between the mean and the placebo condition, the lowest dosage, D0, and the mean and the highest dosage condition, D60. The details of the computations are relatively unimportant, since they are almost universally done by computers. Therefore, we jump right to the ANOVA summary table shown here. The first source of variation, subjects, refers to the differences among subjects. If all the subjects had exactly the same mean across the 2 dosages, then the sum of squares for subjects would be 0. The more subjects differ from each other, the larger the sum of squares subjects. Dosage refers to the differences between the 2 dosage levels. If the means for the 2 dosage levels were equal, the sum of squares would be 0. The larger the difference between means, the larger the sum of squares. The error reflects the degree to which the effective dosage is different for different subjects. If subjects responded very similarly to the drug, then the error would be very low. For example, if all subjects performed moderately better with the high dose than they did with the placebo, then the error would be low. On the other hand, if some subjects did better with the placebo while others did better with the high dose, then the error would be high. It should make intuitive sense that the less consistent the effect of the drug, the larger the drug effect would have to be in order to be significant. The degree to which the effect of the drug differs depending on the subject is the subject's times drug interaction. Recall that an interaction occurs when the effect of one variable differs, depending on the level of another variable. In this case, the size of the error term is the extent to which the effect of the variable drug differs depending on the level of the variable subjects. Note that each subject is a different level of the variable subjects. Other portions of the summary table have the same meaning as in between subjects ANOVA. The F for dosage is the mean square for the dosage divided by the mean square error. For these data, the F is significant, with p equaling 0.004. Note that the probability value for this F test is equivalent to the probability value for a t-test for correlated pairs, with F equaling t squared. Now consider the analysis when all 4 doses are included. With 4 dosage levels, the degrees of freedom for dosage is 3. Since the error is the subjects times dosage interaction, the degrees of freedom for error is the degrees of freedom for subjects, 23, times the degrees of freedom for dosage, 3, and is equal to 69. Here is the ANOVA summary table when all 4 doses are included in the analysis. the effective dosage is significant, p equals 0.003. In the Stroop interference case study, subjects performed 3 tasks: naming colors, reading color words, and naming the ink color of color words. Some of the subjects were males, and some of the subjects were females. Therefore, this design had 2 factors: gender and task. Gender is a between subjects variable, since the male subjects were not the same subjects as the female subjects. Tasks is a within subjects variable, because each subject performed all 3 tasks. The ANOVA summary table for this design is shown here. The computations for the sum of squares will not be covered, since computations are normally done by software. However, there are some important things to learn from the summary table. First, notice that there are 2 error terms, one for the between subjects variable gender, and one that is used for both the within subjects variable task and the interaction of the between subjects variable and the within subjects variable. Typically, the mean square error for the between subjects variable will be higher than the other mean square error. In this example, the mean square error for gender is about twice as large as the other mean square error. The degrees of freedom for the between subjects variable is equal to the number of levels of the between subjects variable minus 1. In this example, it is 1, since there are 2 levels of gender. Similarly, the degrees of freedom for the within subjects variable is equal to the number of levels of the variable minus 1. In this example, it is 2, since there are 3 tasks. The degrees of freedom for the interaction is the product of the degrees of freedom gender, which is 1, and the degrees of freedom task, which is 2, and is equal to 2. Within subjects ANOVA makes a restrictive assumption about the variances and the correlations among the dependent variables. Although the details of the assumption are beyond the scope of this lesson, it is approximately correct to say that it's assumed that all the correlations among variables are equal, and all the variances are equal. The table shows the correlations among the 3 dependent variables in the Stroop interference case study. Note that the correlation between the word reading and the color naming variables of 0.7013 is much higher than the correlation between either of these variables with the interference variable. Moreover, as shown in the table, the variances among the variables differ greatly. Naturally, the assumption of sphericity, like all assumptions, refers to populations, not samples. However, as it is clear from these sample data, the assumption is not met here in the population. This table shows the correlations among the 3 dependent variables in the Stroop interference case study. Note that the correlation between the word reading and the color naming variables of 0.7013 is much higher than the correlation between either of these variables with the interference variable. Moreover, as shown here, the variances among the variables differ greatly. Naturally, the assumption of sphericity, like all assumptions, refers to populations, not samples. However, it is clear from these sample data that the assumption is not met in the population. Although ANOVA is robust to most violations of its assumptions, the assumption of sphericity is an exception. Violating the assumption of sphericity leads to a substantial increase in the type 1 error rate. Moreover, this assumption is rarely met in practice. Although violations of this assumption had at one time received little attention, the current consensus of data analysts is that it's no longer considered acceptable to ignore them. A correction is to multiply the degrees of freedom by a quantity called epsilon. There are 2 commonly used methods of calculating epsilon. The correction called the Heinfeld, or HF, is slightly preferred to the one now conventionally called the Geiser greenhouse, or GG, although both work well. The GG correction is generally considered a little too conservative. The calculation of these corrections is complex and best left to computer software. A final method for dealing with violations of sphericity is to use a multivariate approach to within subjects variables. This method has much to recommend it, but is beyond the scope of this text. Often, performing in one condition affects performance in a subsequent condition in such a way to make within-subjects design impractical. For example, consider an experiment with two conditions. In both conditions, subjects are presented with pairs of words. In condition A, subjects are asked to judge whether the words have similar meaning. In condition B, subjects are asked to judge whether they sound similar. In both conditions, subjects are given a surprise memory test at the end of the presentation. If condition were a within-subjects variable, then there would be no surprise after the second presentation, and it's likely that the subjects would have been trying to memorize the words. Not all carryover effects cause such serious problems. For example, if subjects get fatigued by performing a task, then they would be expected to do worse on the second condition they were in. However, as long as half the subjects are in condition A first and condition B second, the fatigue effect itself would not invalidate the results, although it would add noise and reduce power. The carryover effect is symmetric in that having condition A first affects performance in condition B to the same degree that having condition B first affects performance in condition A. Asymmetric carryover effects cause more serious problems. For example, suppose performance in condition B were much better if preceded by condition A, whereas performance in condition A was approximately the same, regardless of whether it was preceded by condition B. When this kind of carryover effect is possible, it is probably better to use a between-subjects design.